Hello everyone. In this video, we'll be covering concepts from the course of Chemistry 1412, also known as General Chemistry 2. So the concepts we're covering today are going to be acids and bases, autoionization, pH, Bronsted-Lowry, and Lewis buffers. Arrhenius acids and base definition. This is the earliest acid-base definition which classifies these substances in terms of their behavior with water. An acid is a species that increases in the concentration of H+, and a substance that dissociates to yield H3O+. So we have H+, when combined with water, will produce H3O+. A base is a species that increases in OH- and dissociates to yield OH- in water. When the acid reacts with a base, they undergo something called neutralization. So we have our acid, which is our H+, plus our base, which is our OH-, and we're going to produce water, which is a neutral substance. And for this reaction, the delta H is going to be negative 55.9 kilojoules. Strong and weak acids. A strong acid dissociates completely into ions into water. So we have HA, which is going to represent our acid, and this can be in gas or liquid, plus water, which is a liquid, and it's going to produce H3O plus A-. This is just going to be the general formula or reaction for a strong acid dissociation. A dilute solution of a strong acid contains no HA molecules. A weak acid dissociates slightly to form ions in water. So we have our acid, which is our HA, in water, and it's going to produce H3O+ and A-. So we notice that it's the same formula, however, you have to keep in mind that it's only slightly dissociating. In a dilute solution of a weak acid, most HA molecules are undissociated. So we have a Kc of H3O+ times A-, so our products, divided by the concentration of our reactants, which is the acid and the water. And it's going to be a very small value. The acid dissociation constant, so Ka. So Kc, like we said before, is the concentration of our products, which was the H3O+ and the A- over the concentration of our reactants, which is the HA, our acid, and the water. For Ka, we're going to have Kc times water. So we're taking that water from our denominator and we're multiplying it times our Kc. So Ka, since we got rid of that water, is now the concentration of H3O+ times A- over the concentration of our acid, so our HA. The value of Ka is an indication of our acid strength. So for a stronger acid, we're going to have a higher concentration of H3O+, which means that our Ka will be larger. So the larger the Ka, the stronger the acid will be. For weaker acids, we have a lower percent dissociation of HA, which means that we're going to have a smaller Ka value. Classifying the relative strengths of acids. Strong acids are going to include hydrohalic acids that are HCl, HBr, and HI. Make sure you keep in mind which ones they are for a strong acid, because we will have some hydrohalic acids for our weak acids as well. So keep in mind which ones we're referring to for a strong acid. We're also going to have oxoacids, in which the number of oxygen atoms exceeds the number of ionizable protons by 2 or more. So if we look at our examples, so for it to be a strong acid, the number of oxygens exceeds the number of protons, which is generally going to be a hydrogen. So we have HNO3. So we have 3 oxygens, we have 1 proton because of the 1 hydrogen, so our oxygen exceeds our hydrogen by 2. Same thing for H2SO4. We have 2 more oxygen than we do hydrogen. And so this is just going to keep going on and on. For HClO4, we have 3 more oxygen than we do hydrogen. So it has to be 2 or more oxygens than there are hydrogens or ionizable protons. Weak acids are going to include the hydrohalic acid HF. So this is going to be what I was talking about earlier. So this is the hydrohalic acid for a weak acid, while HCl, HBr, and HI are the hydrohalic acids for a strong acid. Acids in which H is not bonded to O or to a halogen, so HCN. We also have oxo acids in which the number of oxygen atoms equals or exceeds the number of ionizable protons by 1. So HClO, our oxygen and our hydrogen are equal to each other because we only have 1 of each, so it's considered a weak acid. For HNO2, we only have 1 more oxygen than we do hydrogen, so it's also considered a weak acid. Carboxylic acids are going to be another weak acid. Their general formula is RCOOH. The R is just a group that attaches to our COO. So the COO that I'm talking about is COOH. So our R group here is CH3. So we have our R group, and then we have our COO. For this one, the R group is C6H5, and then we have our COO. So carboxylic acids are also going to be a weak acid. So let's go through an example. Label which of the following are strong and weak acids. So I'm going to move over to our boogie board so that we can work through this example. So for our first one, we had hydrobromic acid. And the part that you have to remember, this is going to go back from General Chemistry 1, is how to develop our formula from our name. So hydrobromic acid is going to be HBr. Hydro shows us the H, bromic shows that it's a bromine, and so we have HBr. HBr is one of those hydrohalic acids. And now the part that you have to remember, does this go to a weak or a strong acid? HBr is going to go to a strong acid. So for part A, we have a strong acid. Now let's do part B. So part B, we have acetic acid. This is a common acid that we also saw in General Chemistry 1. This one is going to be CH3COOH. So hopefully this will spark a memory because we have a COO. When we have a COO, this means that we have a carboxylic acid. And so the general formula, like we said before, is our R group, which is going to be our CH3 with our COO. And you should remember that a carboxylic acid is going to be a weak acid. Okay, moving on to example 3. We had hydrofluoric acid. All right, so hydro, we know that there's going to be a hydrogen, and then fluor tells us that there's a fluorine. So we have HF. So HF, or hydrofluoric acid, is going to be a hydrophilic acid. And remember, we have to identify which ones are strong and weak. So HS is going to be the only weak hydrophilic acid. And then part D. So part D, we had sulfuric acid. And hopefully by this point you know that sulfuric acid is H2SO4. And because we have oxygens and hydrogens, we know it's an oxo acid. And we have 4 oxygens and we have 2 hydrogens. So this means that we have 2 more oxygens than we do hydrogens. So that will tell us that we have a strong acid. And that wraps up this example. Classifying the relative strengths of bases. So strong bases is our first concept. Strong bases include water-soluble compounds that contain O2- or OH- ions. The cations are usually those of the most active metals. So we're going to have the X is going to represent just an element from a group. So our first one is X2O or XOH, where X belongs to a group 1A. And these are going to be metals such as Li, Na, K, Rb, or Cs. So any of these elements can fit into the X. Our second one is XO or XOH2, where our X is going to be from our group 2A metals, such as Ca, Sr, and Ba. Weak bases include ammonia, so NH3, amines, which have the general formula of RNH2, R2NH, or R3N. The common structural feature is a nitrogen atom with a lone pair electron. So what we're talking about are these 2 dots above the nitrogen. So let's go through an example for these. So our first one was NaOH. This should look like our formula of XOH, where X is going to be from our group 1A. And so because Na is one of those, we have a strong base. For part B, we had CH3, 2, CHNH2. This one is a little bit harder just to see off the bat, but if you think about it, it looks like the structure of R2NH. So this is going to be an amine, and because it's an amine, we know that this is going to be a weak base. So this NH kind of gives it away. The next one we had was C6H5NH2. This one has that same structure, so we know that it's an amine again, which means we have a weak base. For D, we had RbOH, which, just like part A, it looks like the structure of XOH. So, this is we check to make sure that our X comes from a group 1A metal and Rb fits that category. So this is going to be a strong base. And then finally, we have BaOH2. This has the structure of XOH2, which is going to be from our X has to be from a group 2A, which Ba fits that category, so we have a strong base. And that answers all of our parts to this example. Auto or self-ionization of water. Water can undergo auto-ionization or dissociation slightly into ions. So we have two water that are going to dissociate into H3O plus and OH minus, where our Kc is going to be the concentration of H3O plus times A minus over the concentration of H2O squared, where Kc is going to be H2O squared equals Kw. So Kw is going to be for water. That's what this W is going to represent. And that's going to be equal to the concentration of H2O plus times OH minus, which will be around 1.0 times 10 to the negative 14. So this is what our Kw is going to represent. In pure water, H3O plus is going to equal our OH minus, which is going to be the square root of 1 times 10 to the negative 14. So it will be 1.0 times 10 to the negative 7 at 25 degrees Celsius. A change in H3O plus causes an inverse change in our OH minus, and vice versa. So if we have a higher H3O plus, we're going to have a lower OH minus. Same thing, if we have a higher OH minus, we're going to end up with a lower H3O plus. We can define the terms acidic and basis in terms of relative concentrations of H3O plus and OH minus, where H3O plus will represent our acid and OH minus will represent our base. In an acidic solution, the concentration of H3O plus will be greater than the concentration of our OH minus. This makes sense. So if H3O plus represents our acid, the concentration of acid should be greater than the concentration of our base in an acidic solution. In a neutral solution, the concentration of H3O plus and OH minus will be equal to each other. And in a basic solution, the concentration of H3O plus will be less than the concentration of OH minus. Again, this makes sense. So our base will be greater than our acid. So our OH minus will be greater than the H3O plus in a basic solution. So let's do example 3. If we are given a measured amount of HCl in water at 25 degrees Celsius, and H3O plus equals 3 times 10 to the negative 4 molar, what is the concentration of OH minus, and is it a neutral, acidic, or basic solution? So let's go to a board and we can begin to work this example out. So we know that that we have it in water, so we can take into account Kw, because remember that's with water, and they told us that Kw is 1 times 10 to the negative 14. Kw also equals to the concentration of H3O plus times our OH minus. So if we're looking for our base, which is our OH minus, we can manipulate this equation, saying that the concentration of OH minus equals Kw divided by the concentration of H3O plus. And we know what Kw is because it's a constant, and they gave us our concentration of our acid. So we can say that the concentration of OH minus equals 1 times 10 to the negative 14 divided by 3 times 10 to the negative 4. This is going to give us, I'm going to go ahead and write it down here, equal to 3.3 times 10 to the negative 11 molar. And this is going to be the concentration of our base. Now we have to compare the concentration of our acid to the concentration of our base to determine whether this is going to be an acidic, basic, or neutral solution. So just by looking at it, we see we have a 10 to the negative 11 and a 10 to the negative 4. So we know they're not equal, so it can't be a neutral solution. Now we're just trying to determine, is it acidic or is it basic? So if this is our acid and this is our base, we have to determine which one is a larger number. Because this has a smaller exponent, we know that our acid is going to be bigger. So this tells us that the concentration of H3O plus is greater than the concentration of OH minus, which means we have an acidic solution. There we go. Hopefully that wasn't too fast and it made sense. So now we're going to talk about pH. So the image that is shown on the screen is going to be a pH scale. So from 0 to right before 7 is going to be considered acidic. Right at 7 is going to be neutral, and from right after 7 up until 14 is going to be basic. The farther you get to the extreme, so the farther you get to 0, you're going to have a strong acid. The farther you get to 14, you're going to have a strong base. The closer you get to the neutral measurement, so the closer you get to 7, the weaker it is. And then we can actually calculate pH by the equation pH equals negative log of H3O plus. This is going to be something really important to remember because you're going to use it a lot whenever you're dealing with solving for pH. So let's go through an example where we actually use it. It says calculate the pH of a 0.06 moles per liter HCl solution. So let's go to our boogie board. So we want to know the concentration of a 0.06 moles per liter HCl solution. Well, first off, we can determine or use the formula to be able to determine whether our answer is correct. HCl is a base, or sorry, not a base, an acid, and it's a very strong acid. So the number needs to be pretty close to 0 because that's where our stronger acids are. And then the moles per liter just tells us that it's molarity, which can tell us that this is the concentration. So we set up our formula. So pH equals negative log of the concentration of H3O plus. H3O plus is going to be the concentration of our acid, which this number fits in. So we can plug that right in there. So we have pH equals negative log of the concentration of 0.06. When we plug that in, we'll end up with a pH of 1.22. And this, we know, makes sense because we have a strong acid. So it's pretty close to 0, which means it's strong. So our math worked out, and it matches the compound that we're working with. Now we're going to move on to Ka and pKa. Ka and pKa have an inverse relationship. The higher the value of the Ka and the lower the value of the pKa. So for example, say we have a strong acid and a weak base. So your Ka is going to increase as your pKa decreases. And same thing for a weak acid. You're going to have a Ka that decreases and a pKa that increases. And this makes sense because before we had talked about Kas. And as you increase in Ka, you're going to have a stronger acid, and as you decrease in Ka, you'll have a weaker acid. And your pK is just going to be the exact opposite of that. So as one increases, the other will decrease. And there's a couple other formulas that we can use dealing with pKa. And that's going to be where we're relating pKa and Ka. So if you're given Ka, but you have to have pKa, you simply plug it into this equation. So pKa is going to be equal to negative log of Ka. And let's say that you had pKa and you need to find Ka. So it's the same thing. You have Ka equals 10, which is because we have a log with a base of 10 to the negative pKa. And that's how you'll be able to flip back and forth between the two variables. The next one is going to be an equation called the Henderson-Hasselbalch, and it's going to be where we relate pKa and pH. So pH equals our pK plus log of our A minus, which is our conjugate base, divided by HA, which is our weak acid. And we'll go more in depth with our conjugate acids and bases a little bit later in this video. So let's work through an example. What mass of NaF must be added to 50 milliliters of a 0.500 molar HF solution to achieve a pH of 3.25? For HF, the Ka is 7.2 times 10 to the negative 4. So we need to figure out what mass of NaF is needed to achieve all of these parameters. So let's go to our boogie board so that we can work this one out. This is one of the more difficult problems because you have to do multiple, or you have to use more than one equation to be able to solve for it. So let's write down kind of what we know. We know that our Ka equals 7.2 times 10 to the negative 4. We know that we have 50 milliliters of 0.5 molar HF. And we know that we have a pH of 3.25. And we need, sorry, let me move this in. And we need to know the weight of HA to be able to get to that pH. So we know that pH equals the pKa plus log of our base divided by our acid. But we don't have pKa, so we can't really plug this in. And the reason why we are using this equation is because we can plug it in and get the concentration and convert it all the way to our mass. But before we can even start that, we have to figure out what our pK is to plug in. And to determine that, we can use the equation pKa equals negative log of Ka, because they gave us our Ka. So we plug in and we get negative log of 7.2 times 10 to the negative 4, and our pKa is going to be equal to 3.14. And so this is going to be what we plug into our equation. So we have our pH, which is 3.25, equals 3.14 plus log of our base, which we don't know. We have NaF here, divided by our acid, which is our 0.5. And we need to solve for this to get our concentration. So when we subtract this over, we get 0.11 equals log of, I'm going to go ahead and put an x here. So x, because we don't know what it is, divided by 0.5. We then can move our log over, and we do that by doing 10 to what is on the other side. So we say that 10 to the 0.11 equals x divided by 0.5. When we do 10 to the 0.11, we're going to get 1.29. That's going to be equal to x over 0.5. We need to multiply both sides by 0.5. So we get 0.644 equals x. So this tells us the concentration of our base. But we don't want concentration, we want mass. So we need to figure out how many grams this is. So if we set it up on a table, so 0.644, the capital M is molarity, so that's going to be moles per 1 liter. 1 liter. And then we can take into account, because we need to get rid of liters, and we can take into account the volume that we have. So we have 50 milliliters, which is going to be 0.05 liters. Our liters will get canceled out, so this will give us 0.032 moles of NaF. But we have to do one more conversion because we need it in grams. So I'm just going to set it up on the table from here. So for every 1 mole of NaF, this is going to weigh about 42 grams. So our moles get canceled out. And I got this 42 grams just from looking at the periodic table. And so you do 0.032 times 42, and you should get about 1.3 grams of NaF. And that would be our answer. So it was a bit difficult because you had to figure out what process to actually take. So it's very important to understand what information they gave you and figure out where you need to get to. And based off of that, you would have to know, okay, well, I need to find the concentration of my base. So given that they gave me pH and Ka and everything, I know that I'm probably going to have to use this equation. However, because I don't have pK, I have to have a second equation to find that. So hopefully it makes sense and you'll be able to work through this on your own. Now we're going to be comparing pH, pOH, and pKw. So pKw, so remember W representing water, equals pH, which is it's kind of the pH of your acid, plus pOH, which is kind of like the pH of your base, equals 14. So when you add the two together, you should get 14. And that's going to be at 25 degrees Celsius. For Kw, remember that your H3O plus and your OH minus are going to give you 1 times 10 to the negative 14. And that's, again, at 25 degrees Celsius. If you're trying to find pH, you use the equation negative log of H3O plus. And if you're trying to find the pOH, you're going to do negative log of the concentration of our OH minus. When you add your pH and your pOH together, you'll get pKw for an aqueous solution at any temperature. Since Kw is a constant, the values of pH, pOH, the concentration of H3O plus, and the concentration of OH minus are interrelated. If our H3O plus increases, our OH minus will decrease. Same thing, if our pH increases, our pOH will decrease. And that's because no matter what, when you add them together, they give you 14. So let's work another example. What is the concentration of H3O plus for a solution at 25 degrees Celsius that has a pOH of 5.64? So let's move to our boogie board. So we have the concentration of H3O plus is what we're looking for. And we have a pOH of 5.640. So we know that pH equals negative log of the concentration of H3O plus. So we have to figure out how to get here to find our concentration. We also know that pH plus pOH equals 14. So by using this equation, we can determine what our pH is to plug into this equation. So we can manipulate it saying that pH equals 14 minus pOH. And they gave us our pOH, which we can plug into this equation. So pH equals 14 minus 5.640, which will give us a pH of 8.36. We can plug that into our equation. So we say that 8.36 equals negative log of the concentration of H3O plus. So now we need to get H3O plus by itself. So we can move the negative over, so this becomes negative and it gets rid of it on this side. And then we need to move the log over, so we have 10 to the negative 8.36 equals the concentration of H3O plus. When we plug this in, the concentration will be 4.37 times 10 to the negative 9. And that would be our answer. So now we're going to move on to the topic of Bronsted-Lowry acid-base definitions. A Bronsted-Lowry acid is any species that is capable of donating a proton, so something that is able to give off an H plus ion. An acid must contain an H in its formula, so keep that in mind. For a Bronsted-Lowry base is any species that is capable of accepting a proton, which requires a lone pair of electrons to bond to that H plus ion. A base must contain a lone pair of electrons to bond to H plus. An acid-base reaction is a proton transfer process. So let's continue. Water is atmospheric, which means that it can act as both a Bronsted-Lowry acid and a Bronsted-Lowry base. Strong acids and bases ionize completely in an aqueous solution, while weak acids and bases are only going to partially ionize. So that is something that kind of relates to our previous example. So remember, strong is going to completely ionize and weak is only going to partially. And now we're going to have the concept of conjugate acid-base pairs. A conjugate pair refers to acids and bases with common features. These common features include the equal loss or gain of protons between the pairs. Conjugate acids and bases are characterized as the acids and bases that gain or lose protons, respectively. In an acid-base reaction, an acid plus a base reacts to form a conjugate base plus a conjugate acid. So we have our acid plus our base is going to form or yield a conjugate base plus a conjugate acid. And I'm going to go ahead and show you a brief video that makes will hopefully make this make sense a little bit better.
So I'll put a minus for losing a proton.
Let me start this over.
In this video, we're going to be talking about conjugate acid-base pairs. We're going to introduce the idea of a conjugate acid-base pair using an example reaction. The example reaction is between hydrogen fluoride, or HF, and water. So hydrogen fluoride is a weak acid, and when you put it in water, it will dissociate partially. So some of the HF will dissociate, and you'll get fluoride minus ions. And then that dissociated H plus ion, so this dissociated H plus ion will get donated to our water. So water then becomes H3O plus, or hydronium. And so this process is in dynamic equilibrium because it can go forward and it can go backward, and eventually those two rates are equal and they're both happening at the same time. So in this reaction, we have a couple things going on, and we're going to think about it in terms of hydrogen ions being exchanged. So if we just look at the hydrofluoric acid and we look in the forward direction, our HF is becoming F minus, and it's doing that by donating or losing. So I'll put a minus for losing a proton. So our HF loses a proton. That forms our F minus, or fluoride ion. And then we can look at that same process happening in the backwards reaction. So if we look at the backwards reaction, which is also happening, the fluoride ion can pick up or accept a proton from somewhere. So it can pick up an H plus. So I'll have a plus, H plus here. And so when fluoride accepts a proton, we reform our HF. So we can see that HF and F minus have this special relationship where you can form one or the other by losing or gaining a proton. And we can see a similar relationship between water and hydronium. So water here, we said water is accepting a proton from HF. So we see that water will gain a proton, and that will give us hydronium. In the reverse reaction, hydronium can lose a proton to reform water. So minus H plus. So again, we have these two species, water and hydronium, that are related to each other by having or not having one H plus. So in chemistry, we call these species that are related in this way conjugate acid-base pairs. So the official definition, or my official definition of a conjugate acid-base pair, is when you have two species that are related to each other. Let's see, two species that are related to each other, related by one H plus. In this case, we have HF and F minus that are related to each other by that one H plus, and so HF and F minus are a conjugate acid-base pair. We also have water and hydronium, which are also related by that one H plus, so water and H3O plus are also a conjugate acid-base pair. You can probably tell from the name, but whenever you have a conjugate acid-base pair, one thing in the pair will be an acid, and the other thing will always be a base. The definition of which one is the acid and which one is the base comes from the Bronsted-Lowry definition of acids and bases. So the Bronsted-Lowry definition says anything that can donate an H plus, so anything that will give away an H plus, is an acid. So we can see that in this case, our hydrofluoric acid is acting as the acid in the conjugate acid-base pair. And that means that fluoride has to be acting as the base. And that makes sense because the Bronsted-Lowry definition of a base is something that will accept an H plus. And that's exactly what it does in the reverse reaction. Your F minus will pick up an H plus and go back to your acid. So we can also look at water and H3O plus. So here, water is gaining a proton or accepting it, so water is acting as a base. And in the reverse reaction, H3O plus is donating a proton, so H3O plus is acting as an acid. The relationship between conjugate acid-base pairs we can write a little bit more generally. So if we represent any generic acid as HA, so this is our acid, we said that an acid is something that donates a proton. So it'll lose the proton, and when it does that, it will form the conjugate base, which is represented by A minus. In the reverse reaction, our base, A minus, can gain a proton and remake our acid, or conjugate acid. So whenever you have two species that have basically the same formula, which we abbreviated here as A minus, except for one has an H plus and one doesn't, then you know you have a conjugate acid-base pair. So let's look at some more examples of conjugate acid-base pairs. We saw above HF, or hydrofluoric acid, its conjugate base is F minus. So here, HF is our acid, and when it loses that proton, we are left with F minus. We saw in the same reaction that water can act as a base. So if water is our A minus, if that water accepts a proton, it forms the conjugate acid H3O plus. The example we've gone through so far, HF, is for a weak acid, but we can also talk about the conjugate base of a strong acid, like hydrochloric acid. HCl is a strong acid, so that means it completely dissociates. So it gives away all of its protons, and when it does that, we're left with the conjugate base, chloride. So even though chloride isn't particularly basic, it's still the conjugate base of HCl. And last but not least, we're going to go through two examples where it looks like we might have a conjugate acid-base pair, but we actually don't. So one example is, what about the relationship between H3O plus and OH minus? If we think of our acid up here being H3O plus, if we lose one proton, we saw that its conjugate base is water. If water loses another proton, we get OH minus. So the difference between these two species here is 2 protons instead of 1 proton. So these two, hydronium and hydroxide, are not a conjugate acid-base pair because they differ by 2 protons instead of 1. And then the last example we'll look at is, we said that fluoride is a conjugate base of HF. So what about the relationship between sodium fluoride and fluoride? And so these two are also not a conjugate base pair, because if we take our fluoride ion and it accepts a proton, we don't get sodium fluoride. They are related by a sodium ion. So by definition, that these two are not a conjugate acid-base pair. So in this video, we learned that a conjugate acid-base pair is when you have 2 species and they have the same formula, except one has an extra proton. So the acid has an extra proton, which it can lose to form the base.
All right, hopefully that was helpful in explaining what a conjugate acid base is. You will be seeing those on your future exams, so I highly suggest that you get a little practice in on them. The next thing we're talking about is acid strength of oxo acids. All oxo acids have an acidic H bonded to an O atom. Acid strength of oxo acids depends on the electronegativity of the central nonmetal E and the number of oxygen atoms around the E. So E is just representing that central element. For oxo acids with the same number of oxygens, acid strength increases as the electronegativity of our central nonmetal increases. For oxo acids with different numbers of oxygen atoms, acid strength increases with the number of oxygens. So these are true rules that can help you determine the strengths of oxo acids. The relative strength of oxo acids. So this is just kind of explaining what we said earlier. So it's showing how the strength is increasing from left to right. The electronegativity increases as we go from left to right, so the acidity also increases. And the main difference that we have is the element that is attached to our oxygen. So as we see from I to Br and from Br to Cl, our electronegativity is increasing. And then for part B, we go from having O to Cl all the way from O to a lot more oxygens. So the number of oxygens is increasing in our second, which means our acidity is also increasing in our second example. Weak bases. A Bronsted-Lowry base is a species that accepts H+ for a weak base that dissolves in water. So this is kind of what we explained earlier. The base definition, or base ionization constant, is given by Kb. So Kb is going to be the concentration of our Hb, which is our one of our products, times the OH- divided by the concentration of our base. Note that no base actually dissociates in solution, but ions are produced when the base reacts with water. Ka and Kb for a conjugate acid-base pair. So we have HA with water that produces H3O+ and A-. This is going to be for an acidic solution. And then we have it reversed slightly, but we have a OH- as our product. When we cancel out the items that are similar on the different sides of the equation, so our A- on our product side for our reaction 1, and the A- for the reactant side on reaction 2, they're going to get canceled out, and we'll be left with H2O yields H3O+ and OH-. The Kc, which hopefully will you'll remember from a previous chapter, for the overall equation is going to be the same that we discussed in our earlier chapters. So you take the K from the different reactions, you multiply them, and you'll get your overall Kc. So our Ka, which is going to be our H3O+ times our A- over HA, times our Kb, which was our HA times OH- divided by A-, is going to be equal to Kw. So it's not really a new concept, it's just making you understand how we were able to get our Kw from our previous slides. So our like items will get canceled out, and we'll end up with just H3O+ and OH-. So what you should get from this is that by multiplying our Ka times our Kw, we can get Kw. The relationship is true for any conjugate acid-base pair. Lewis acid-base definition. A Lewis base is a species that donates an electron pair to form a bond. A Lewis acid is any species that accepts an electron to form a bond. So we have our base, and it's going to accept the electrons. The acid is going to accept them, and they're going to form that base. And same thing, you can tell which one is the base because it's willing to donate to that acid. The Lewis definition views an acid-base reaction as the donation and acceptance of an electron pair to form the covalent bond. So keep in mind the difference between the Bronsted-Lowry acid bases and the Lewis acid-base definitions. You will have to know the difference for your exams. A Lewis base must have a lone pair of electrons to donate. Any substance that is a Bronsted-Lowry base is also going to be a Lewis base. Know how to relate these two to each other so that you can compare and contrast. A Lewis acid must have a vacant orbital, or be able to rearrange its bonds to form one, to accept a lone pair, and to form a new bond. Any substances that are not Bronsted-Lowry acids are going to be Lewis acids. A Lewis definition expands the classes of acids. And now we're going to start talking about buffers. An acid-base buffer is a solution that lessens the impact of pH from addition of an acid or a base. So if I have a solution and I want to add more substance to that solution without changing the pH, that is when a buffer comes into play. An acid-base buffer usually consists of a conjugate acid-base pair, where both species are present in an acceptable quantities in solution. An acid-base buffer, therefore, a solution of a weak acid and its conjugate base, or a base and its conjugate acid. How a buffer works. The buffer components, which are HA and A-, are able to consume small amounts of OH- and H3O+ by a shift in the equilibrium position. So adding H3O+ reacts with the CH3COO-, causing a shift to our left. By adding OH to our left side, reacts with the CH3COOH, causing a shift to the right. The shift in equilibrium position absorbs the change in the concentration of H3O+ or OH-, and the pH will change slightly. Preparing a buffer. Choose the conjugate acid-base pair. The pKa of the weak acid component should be close to the desired pH that you're looking for. Calculate the ratio of the buffer component concentration. We can do this by using the equation pH equals pKa plus log of your base divided by your acid. So you can use that to determine the concentration of your acid or your base. Determine the buffer concentration and calculate the required volume of the stock solution and or masses of your components. And then mix the solution and correct the pH. Buffer capacity. The buffer capacity is a measure of the strength of the buffer, its ability to maintain the pH following addition of a strong acid or a base. The greater the concentrations of the buffer components, the greater its capacity to resist the pH changes. So this is going to be an important key in determining whether something is going to have a higher or lower buffer capacity. The closer the component concentrations are to each other, the greater the buffer capacity. So for instance, if I have 1 molar of each, it's going to have a higher capacity than something that has 0.5 molar and 1 molar. And then finally, buffer range. The buffer range is the pH range over which the buffer is effective. A buffer range is related to the ratio of the buffer component concentrations. The closer the HA and over A- is to 1, the more effective the buffer is. If the component is more than 10 times the other, the buffering action is poor. Since log 10 equals 1, buffers have a usability range of plus or minus 1 pH unit of the pKa of the acid component. So we're going to work an example where we're trying to determine what that pH range is for it to be effective. The indicator propyl red has a Ka of 3.3 times 10 to the negative 6. What would be the approximate pH range over which it would change color? So we want to know what that buffer range is. So let's go to our boogie board. So we had a Ka of 3.3 times 10 to the negative 6. And we want to know that pH range. We were told that plus or minus 1 of our pKa, this will give us our range. So the first thing we need to do is convert our Ka into pKa. And we do that using pKa equals negative log of Ka. So this is going to be equal to negative log of 3.3 times 10 to the negative 6. So our pKa equals 5.5. For our range, we have to do plus or minus our pKa. So 5.5 plus or minus 1. So our pH range equals 4.5 to 6.5. So this is the range in which our pH can be. And that pretty much wraps up our video for today. Hopefully this made sense. Other resources that you can use is Khan Academy if you're still struggling with conjugate acids and bases or calculations that we've done today. I highly suggest that you make flashcards or whatever way that you can memorize best on how to determine the difference between Bronsted-Lowry and Lewis acids and bases. Also remember the rules on how to do conjugate acids and bases. That is all that we have today. Thank you and best of luck.